Hi guys, welcome to this video. Today we'll be discussing a really interesting problem which is called the Buffon's needle problem, which was first posed by Buffon, obviously, which is this guy apparently. Uh, I don't know. So the problem is as follows. So we have lines that are parallel and 2 units apart, and we drop matchsticks. And the problem asks us to calculate the probability of this dropped matchstick intersecting with any of the lines. So of course the matchstick can intersect with only one line at once, because it's you get it. So the factors that affect the intersection are like the distance of the matchstick from the center of the matchstick from the line, and the angle it makes with the horizontal level. So I think there are two ways to solve this problem. One is using calculus, and the other one, you'll get to know. I'll be solving this problem using calculus. So let's get started. So this is the matchstick that I was talking about. So this is 1 units in length. So of course the distance, this distance right here is half. So we can define two parameters right here. One is theta, which is the angle with the horizontal level, and this d, which is the distance from the line, the center distance from the line. So of course d varies from 0 to 1, because this whole thing is 2 units, but when you're in this area, the distance is now from this line, and theta is the acute angle with the horizontal level. So if it's that way, then it's that angle. Okay, so now the condition. So now, when does the stick intersect the line? Okay, so this distance right here should be greater than that distance in order for this line to this matchstick to intersect the line, and that is the condition that we get. Half sine theta, which is this length right here, should be greater than d. So how do we solve this problem? So one way is to graph this thing right here, this inequality in theta d space, which is what we are going to do. So this is the graph plotted, the condition. So this region right here represents the region that satisfies the inequality. Okay, so what we have here is, this is theta d space. Okay, d varies from 0 to 1, and theta varies from 0 to pi by 2. Now what is this? What does this space represent? So every point in the space is a tuple, which is theta d. Okay, what is that? That is a sample point. So this is the sample space of the whole event. The event can happen in all these ways. The event of dropping a matchstick on the on line separated by 2 units. All the possible configurations of that event are there in this space, and only a small part of those all those configurations satisfy the event that we want, which is the matchstick intersecting with some line, and that region is represented by this region. That condition is represented by this region. So the probability of that event happening is the area under this curve divided by the whole sample space, or the area of the sample space. So that is what we do. So what are we gonna do? This is an elementary problem. Finding the area under this curve is very elementary. So we do that. We write the integral, and this is pi by 2 into 1, which is the whole thing, whole rectangle, and what we get is 1 by pi, which is really interesting because I don't know why, but pi pops up here, and this gives us a really good way to approximate the value of pi. So this was the first method of solving this problem. Yeah.
Alright, so the second method is called the Barbier's proof, and it is done using expectation values and probability. So now, well, let's just say that this is these are the lines we have, right? And these are 2 meters apart, and there's a small needle inside it which is 1 meter long. Okay, and now what is the number of expectation values of intersection this needle has with the lines? So, well, the expectation value is the number of intersections into the probability of those number of intersections. So basically 1 into probability of one intersection plus 2 into probability of two intersections, and so on. Now, as it turns out that as the needle is only 1 meter long, it cannot have more than one intersection. Unless it is horizontal and on the line, then it will have infinite number of intersections. But the probability of that happening is basically zero. So we can count that also out. So basically the expectation value of this is just P1. And now let's just say that this is expectation value of a 1 unit needle, right? Okay, so and now why are we using expectation value and not directly just probability? Well, that is because expectation value has this amazing property, which is the linearity of expectation value, right? Okay, and similarly this e of n times x is n times e of x. And now if you see, let's say we have a needle which is 1 unit long. We can basically convert this, and this can be x units long and this can be 1 minus x units long. Well, the expectation value or the probability will not change even if we do, oh sorry, yeah, x plus 1 minus x, if we take the expectation value of these two separately. And now if you think about it, it does not have to be in the same line. You can basically just plot two separate two separate needles and join them, and it will still have the same expectation value, right? And then you can do this as much as you want. You can keep on splitting because, well, eventually you can split e of x into two more, e of y and e of x minus y, as long as all of these values sum up to 1, right? So effectively we can create polygons. And now for the sake of simplicity, let's say we create regular polygons, right? So, and let's say we create a polygon of side n, right? Well, if we keep on increasing the value of n, and as n tends to infinity, the polygon sides get smoother and smoother until they basically just become a circle. And the thing is that, like, now we have a needle where the total length is 1 unit, which basically implies that the perimeter of the circle is 1 unit, which means that 2 pi r is 1 unit, or the radius is 1 by 2 pi units. And now the thing is that the expectation value of this circle is the same as the expectation value of a needle of 1 unit, which is basically the probability of one intersection of that needle. And now finding the expectation value of the circle, as it turns out, is much easier than finding the expectation value of the needle. So now let's say these are the two lines which we have, which are spaced at 2 units. And now let's just look at between these two lines, right? Okay. And now if you notice that a circle can have either 0 intersections, 1 intersection, or 2 intersections. Now 1 intersection is very rare. The probability is basically 0 because that's only at 2 points in this entire region. So we can basically say that the probability is 0, so we can neglect this. Now for 2 intersections, well, now since we're only looking at this area, let's say that more than half of the circle is within this area. Okay, so now this to this, right? This is the region we're covering. This is the center and this is the center. Now the circle intersects this point. So basically this radius is 1 by 2 pi. The length, the distance of the center from one of these lines where the circle still intersects the line, well, the center can move at most a distance of 2 pi, where the circle is still intersecting this line, or 1 by 2 pi, sorry. And similarly from this edge also, the center can move at max 1 by 2 pi, right? So basically we have 1 by 2 pi plus 1 by 2 pi as the total distance that the circle can move such that it is still touching. And what is the total distance between the lines? Well, that is 2 units. And now since we have 2 intersection points, so that is 2 into probability of 2 intersections. And well, and that is the expectation value of the circle, which is 1 by pi. And that is also the intersection, and that's also the expectation value of the needle, which is also the probability of the needle intersecting the line. So yeah, there you have it. The answer is 1 by pi by the Barbier's method.